session. It's electronic session, and we have 6 presenters, and the time limit for each presenter is 15 minutes, including discussion. So approximately 10-12 minutes for presentation, and after that discussion. If you come to the finish line, I will show such signs, okay? How much time left, and will fit in time. So the first presentation is from our university, Kaunas University of Technology, and Professor Linas Vilenis will present the topic ultrasonic air-coupled transducer output impedance measurement technique.
Hello everyone. I'm presenting the research related to output measurement of the ultrasonic transducer, and the major task in this case was the output impedance measurement. Actually, it is the joint work with Thomas Gomez Alvarez Arenas. He is from Spain, from Spain Institute for Automation and Ultrasonics, and this is their logo. It is Spanish Academy of Sciences. When it comes to ultrasound, there are several types of ultrasounds. This time we're analyzing air-coupled ultrasound. So basically there are 2 transducers located in front of each other. Mainly the air-coupled ultrasound is working in this way because the losses when you are trying to enter the signal from the air into a solid material are large. So the most frequently used mode is when you use the transmission ultrasound. And this is the signal that you receive from the opposite end. And just to give a brief note, it is really wideband transducer developed by our colleagues from Spain. And this is how the measurement is done. We first measure the signal without the material inserted, and then we insert material. This is how the signal looks like when the signal had multiple propagations within the material. And by going into frequency domain and dividing the measured signal by the reference signal, we obtain the magnitude response and the phase response. And then when we fit the mathematical model of the material, we get material properties: thickness, density, elastic properties of the material, even the porosity if it is membrane. And you can see that essential is signal-to-noise ratio, because the deeper in the valley we are able to measure, the better we estimate the material properties, because the model fits better. Otherwise, you just have the noise here, and of course the guess will be not the correct one. And of course, setup was favored for us, because receiver is not operating in transmission mode, so we had all the freedom to do the optimization. But in order to do the optimization, you need to match the transducer both for the transmission part and both for reception part. And in order to do that, you need output impedance of the transducer. When it comes to noise, it's not just matching, but of course you need to match in the noise sense. Every amplifier that you use possesses so-called optimal impedance. That is the impedance that is optimal in the noise sense. The least noise is added from the source, and least noise added is from the amplifier, current noises in particular. So when it comes to impedance measurement, the idea is pretty simple. You need just current through your unknown impedance and the voltage on the clamps of the impedance element that you are measuring. And this is the simplest setup, which is called IV measurement, when you are using reference resistance and you measure the voltage drop on that reference resistance. Unfortunately, it has a disadvantage, because the upper part of the measurement instrumentation is floating, so you need to measure differential voltage on that reference resistors. And of course, you need 2 channels, which might look like given, because if you need voltage and current, so what else you can do? There is also another technique which is called auto-balanced bridge. It is more convenient because now it is not floating, so the output U2 is proportional to the current, so we can measure current conveniently. But in this case, the ground is floating, and as you can see, the ultrasonic transducers usually have coaxial connector, and usually they are mounted in some fixture for positioning, for measurement. So in order to measure the impedance, you need to dismantle the transducer to disconnect the ground because you have an ABB technique, and ABB technique has least errors in the measurement. We propose not new, it is standard technique, but we decided to use this technique for complex impedance measurement of the ultrasonic transducer. And the idea is pretty simple. You just measure the output voltage of the transducer in two load conditions. One is RL, low load, more or less low impedance load, and R, high impedance load. These are the equations that you have, and then the equation for the impedance measurement turns that simple. I want to draw your attention that despite there can be some amplifier because the signals might be lower, despite there will be some transmission which is put in equations like K, you can see that in final equation K vanishes, so you do not need to calibrate the transmission coefficients of the ultrasonic of the measurement channel, so it is a single channel and no need for correction coefficient K. And of course, what was important for us, it has grounded connection for the unknown impedance. This is how it was arranged. These are the transducers, how they are used in measurements. So they are attached, and you can see that they are grounded. One of the transducers is used for transmission, another is used for reception, and the whole circuit is on the right side. So you can see how the whole system looks like. So we need PC to control what we are sending, then the controller of the pulsar, then pulsar itself, transmitting transducer, receiving transducer, the preamplifier, AD converter, and of course acquisition, buffer memory, and everything goes to PC. If to compare to conventional ultrasonic non-destructive testing or ultrasonic system setup, you can see that everything is the same. In ultrasonic system, we always have the excitation channel, we have the reception channel, because those are used both for imaging and for transmission measurements. So that's one more advantage, because we don't need additional instrumentation to do the measurements. We can use the same ultrasonic system for the measurements. One more improvement that we have used is the sine wave correlation. Sine wave correlation is used when you have sinusoid which is noisy and you want to measure the signal with high accuracy, that is to take all the information that is available. And the idea is very simple. You have artificial sinusoid and you are trying to fit both the frequency of that sinusoid and magnitude and DC offset and the phase of that sinusoid. And then this is how it looks mathematically. And then you are using this sinusoid as your measurement result, because that sinusoid, in order to generate this model, you need amplitude, or magnitude rather, you need phase, and you need the frequency. One more improvement, or actually we were cheating, we were not approximating the frequency, because once it is us who are transmitting the signal, then we know what is the frequency. You might say frequency is always known because we are turning the knob of the generator. No, this accuracy is not enough. Usually then you need 4 parameters fitting, but in that case the clock is coming both for transmission part, for generation of the excitation signal, and both for reception part. And that's the advantage that we have used usefully. And you can see that these are the errors of sine wave correlation, how quickly they go down. So if more than 3 periods of the sine wave you have, so you don't need to care about how many periods you are fitting into the acquisition signal. And of course, in order to get the phase, we use cosine and sine. So we use two functions, cosine and sine function. And from those we have real part, imaginary part, and from those we obtain what we need. These are the signals that we used for testing, because the pulse signal is the conventional signal that is used in ultrasonic measurement systems. Chirp signal is getting popular, but it is not widely used. And of course, we used the sets of the tone bursts, which every tone burst in a set was different fill-in frequency. And one more that we used not rectangular, because you see both first three signals, they are rectangular excitation. The last one is analog signal, that is pure sinusoid. But that sinusoid was long. That was simulated just to see what would happen if we are using simple impedance measurement technique, because in impedance measurement, this sinusoid never ends. But we needed those sinusoids short, because all three signals, they were selected in such a way that if you have the distance between the transducers, so physically, the physical length of those signals was such that they were not in multiple reflection, they were fitting in the distance between the transducers. Meanwhile, the last one, the sinusoid, which was infinite, you can say, it was undergoing multiple reflections between the receiving transducer, transmitting transducer, and it was bouncing in between those transducers multiple times. Since we wanted some reference measurement, so we took Bankier impedance analyzer. I deliberately put the price for this impedance analyzer because it is really expensive piece of equipment, and besides it has this continuous sinusoid. But because we were measuring as an input impedance, because this time we measured input impedance, and there was no receiving transducer, so there was no this multiple bouncing. So more or less we were able to measure the impedance with this device. But what is not convenient, that device is expensive. And these are the results with continuous wave sinusoid. As expected, we have interference produced. Then the results of continuous wave tone burst. And for the comparison, the continuous line is the reference measurement, and the dots, they are for the measurements using the tone burst. You can see that almost perfect match. And if somebody interested in errors, so these are the magnitude errors, more or less 5%. Chirp, it is another signal. So for chirp we get 10% errors, and for pulse we have 30% error. The reason is very simple, it has much lower energy. And this is the analysis for the errors, so lower signal-noise ratio, but you have to keep in mind that excitation was with 0.3 amplitude. So we can easily go to 30 volts, then the gain goes from 40 dB to 0 dB, so we can easily gain 40 dB. Then another idea was that maybe the reason for the errors is the fluctuations in the air, so if there is some fluctuation, so there might be some errors. So we carried out experiment when there was no hood that usually is used for protection against the wind, and these are the results, so more or less about 1.5%. Then another idea was maybe resistances, they are not optimal, but it turns out that within the passband it is just 0.1% and totally 5% errors. And then finally it turned out that it is itself, the impedance variation itself, because impedance variation with temperature, we made 3 measurements when the transducer was held in hand, and then we left it cooling, so you can see that up to 25% variation in the impedance. So to conclude, the output impedance measurement technique proposed is simple, requires only one acquisition channel, there is no need for reference resistor adaptation because the dynamic range of sine wave correlation is very large. No need for reception channel calibration, conventional ultrasonic signal system can be used, and conventional excitation signals can be used. That is no need for those sinusoids that are more or less complicated to produce. And the measurement is ground reference, and accuracy that we think we have received is 3%. Thank you.
Thank you. So, please ask your questions. Can I ask you, did you have some challenges during this research, or everything went easy?
Not that easy. First of all, it was quite hard to get 0.3 volts because our system is capable to produce 600 volts for excitation. Usually in ultrasound it should be this way. So first we had to realize how to do this attenuation of the signal. And then, of course, the processing itself, you need, because we wanted it automated, so how to locate the signal, how to gate it, how to truncate, and so on.
Mm-hmm. Thank you. No more questions? Okay, thank you. So, next presentation is from Denmark, and the presenter Arnold Knott will make presentation on topic a high voltage low power switch capacitor DC-DC converter based on gallium nitride and silicon carbonate devices for LED driver.
Yep. Thank you very much for the introduction. The work was conducted between the three of us. One of our PhD students here, Lin Fan, who couldn't be here today, and then the
You better stand outside
supervisors.
first.
I have to go away from that microphone.
No, but because the light is coming, we are
Alright.
making translation.
And the supervisors, that's me and Ivan, so two guys doing the drumming and one guy doing the work. So I hope I can do the drumming today correctly. The agenda for the talk is I'm going to look into the objectives first, the circuit design that we did, how we synthesized it, how we implemented it. I was mainly the PhD student doing that work, how we verified it, how we measured the results, and concluding the talk. The objective was to convert the AC mains down, the European AC mains down, to a lower voltage in a multi-stage approach for LED lighting application purposes. So for LED light bulbs, so it's a rather low power, 10 watts only, and it was supposed to be on the high efficiency side. We wanted to have at least 95% efficiency, and we were shooting especially for high power density, more than 4 watts per cubic centimeters. The circuit design approach we have been chosen for this design here was a switch capacitor circuit, converting the input voltage from C4 here into an output voltage of C3, dividing by a factor of 2, and intermediately storing the energy in the flying capacitor C2 here. The circuit is operating in two main operation states. In one of the main operation states, you have Q1 turned on and diode T1 turned on, charging the flying capacitor C2 and converting the energy to the output C3. And the other one, you're using the energy you just stored in C2 and freewheel it out to the output to C3, and then you ideally go back. In between, you have two intermediate operation stages, transition stages, where the voltage across Q1 and D1 is building up and not just jumping from 0 to the mains voltage, but it has to build up because of the parasitic capacitances and parasitic charges in those two components. And the same vice versa over here for Q2 and D2 when you have to charge this voltage up. The waveforms, especially on the gates, controlling the two devices up there, and must be a dead time in between, so you're not short-circuiting the capacitances. Otherwise, you would lose all the energy you have stored in them. And accordingly to that, the drain source voltages would have an overlap while they're building up or charging down. The flying capacitor voltage is mainly linear charging or discharging in the main operation stages, and during the parasitic or the transient stages, you have an exponential first order relationship of the voltage here, and the current is spiking quite a lot while you are charging and discharging the capacitor. The same goes for the trans capacitance from the input to the output. You also have quite some current spikes in those two guys, and also the voltages are similarly. And for synthesizing the circuit, then we've been mainly focusing on trading off the switching losses that we had in the circuit here. It's often in power electronics, it's the trade-off between switching losses and conduction losses you have to look into. You have the gating losses, and then we've been looking into which components we have available to implement the whole circuitry. One argument was looking especially at the power semiconductors, the conduction directions, which voltage, which current is positive, negative, which one is going in which direction. We looked into the drive needs, which are different for different semiconductors, conduction losses, switching losses, gating losses, and especially for achieving high power density, you definitely want to have very, very small footprint area, so you can squeeze things together at the end of the day. When we looked into the voltages and the currents, which I just presented to you in the circuit operation here, we realized that it's only the low side devices which actually can be replaced by a diode, and the other ones have to be switches because they would be conducting in both directions, but the diodes would only be conducting in one direction, so the low side devices are candidates for diodes. I'm not saying we've chosen them based on that criteria yet, but at least they're candidates. The upper, the two high side switches, Q1 and Q2, are not possible to implement as diodes. You need to use transistors for that. A pretty simple statement actually. For the diodes, you don't need a gate driver, so you're also eliminating all the gating losses for the diodes. So you're saving on that one. You're also saving on circuit complexity if you're using power diodes instead of transistors. On the conduction losses, you have a disadvantage if you look into the diodes, because the forward voltage of diodes is rather high compared to the forward voltage you would have across the transistor drain source region. So you're actually losing on that one. So you have to win those losses somewhere else again. This is a rather high voltage application, but a rather low power application. We're only speaking about 10 watts, and the conduction losses are also proportional to the current that you are conducting through the diode. So it might or might not be a good idea to have that double checked. The switching losses then. The switching losses are rather interesting, which are depending quite a lot on the parasitic capacitances and charges, which I mentioned earlier from the devices, especially the output charges of the devices, COSS, for example, for the transistor. And we figured out that for the available components on the market, we had about a factor 5 or 6 less in the diode. So here we could actually save again what we lost in terms of the conduction losses. I mentioned it earlier already. Diodes don't need a gate driver, so you are eliminating totally the gating losses, the gate drive losses for the diodes. In terms of footprints, we ended up choosing some diodes which were actually bigger than the transistors, but also taking into account again that you don't have a gate driver. The amount of components, the footprint area you need for the gate driver plus the transistor was actually bigger than the diode itself. So that was also another argument for using two diodes in the low side, for the low side devices. You can hear already where it's going. We implemented the low side one with the diodes. We've chosen two silicon carbide diodes here. We've chosen gallium nitride transistors up here. Those transistors need a gate driver, which needs capacitive isolation because it's jumping up and down here with the signals here and there. So they're referenced to their respective source. And that gate driver again needs a power supply. So that supply is coming from down here, where the gate driver itself was capacitively isolated across the barrier inside the driver here. We had an inductive isolation in the supply for those drivers here. So that was a little converter there extra. The part numbers are down there, how we isolated those devices. And for the main power stage, I'm not going to walk you through all the boring table here. That's the analysis of the losses, the conclusion of how we ended up with these specific devices here. That's more in the paper, and you can read through all that in the paper here. The basic point is here which devices we've been chosen. We have chosen the EPC GaN transistors. We've been chosen the silicon carbide diodes down here. And with the capacitors, we made a little bit of an experiment, especially with the flying capacitor C2 there. We've optimized it for two different operating regions. The 3 microfarad was for heating for high power density, and then the 9 microfarad was for the best efficiency, and the 6.1 is a trade-off in between. We verified the whole circuit in the lab through different means. First of all, here's a picture of how we implemented it, the top side and the low side. You can see the very, very tiny GaN devices here. This is a BNC connector here for reference. These are the tiny GaN devices, the gate driver for the GaN devices, the flying capacitor here on the top side. And on the bottom side here, we've got all the other capacitors here, and also on the top side, the silicon carbide diodes. You can see those are bigger than the GaN transistors here, but also taking the gate driver into account. You save area actually by using those two silicon carbide diodes there. That's the lab setup on how we connected it. We're using a lot the thermal camera to verify the temperatures of the devices. We're using precision multimeters for measuring efficiencies, a high-speed oscilloscope, electronic loads, and some waveform generators to generate the pulses for the whole test setup. The converter and the test is in the cable mesh here, somewhere behind all the cables down there. The operation of the circuit was first verified with the oscilloscope. This transition here is one of the fastest we had with about 50 volts per nanosecond, so that should be state-of-the-art switching speeds. We measured the step-down ratio, which was supposed to be a 2-to-1 converter, and we were hitting pretty well in the 2 area with some tolerance around it. When we also take into account that we've tested with 2 different input voltages, 374 volts, which is the maximum occurring one with the tolerances of the grid in Europe, and a 300 volt just for testing it also at a different point. And the 3 different colors here offer the 3 different experimental operating regions. Efficiency, major point, getting the efficiency rather high, efficiency versus output power. We've been looking up to 10 watts, but we were also able to dim it down to 1 watt only, so that's a 10-to-1 factor of the output power, and the efficiencies are at no point lower than the about 93% here, and hitting all the way up to 99% or close to 99% in the best case. We've experimented a little bit with switching frequency, also for the 3 different cases. This was the highest power density, remember, 3 microfarads only. So it's only 1 capacitor, we mount 3 of them in parallel. Here you've got 2 of them. This one is the one for the highest efficiency, as I've shown you before. You're hitting on the high side and the efficiency here. Here the efficiency is lower, power density is bigger because you're losing less space or less volume for the implementation of it, and 6 microfarads was the trade-off in between. The peak efficiencies which we've measured for the 2 different voltages we've been testing with, plotted against the power density, we were aiming for 4, which is somewhere out here on that graph here. So we were going ways further than we expected to be, nearly twice as much as we wanted to, and we had the good efficiencies above 95% that we expected to have, or that we were designing for. A good way of verifying the design is also keeping an eye on the temperature. We are usually always having a thermal camera mounted on top of our designs. For the high power density design, we were allowing a rather high temperature rise, 33 degrees Celsius above the ambient temperature, 22 degrees Celsius. And for the highest efficiency design here, we were going rather low on that one. We were at only 13 degrees above the ambient temperature, which was also about 23 degrees down there. Yeah, and that brings me to the conclusion of the talk. We've been showing the operation of a 2-to-1 switch cap power converter with the 2 main operating stages, the 2 transition stages. We've been synthesizing the whole circuit, implementing it using 2 GaN power transistors and 2 silicon carbide power diodes. We looked at the trade-offs, switching losses and conduction losses, especially between power diodes and transistors. And we verified the whole thing experimentally with respect to power density, with respect to efficiency, temperature rise, operation, and maximum power, the maximum temperature. The quantified results, the numbers we were achieved, the 2-to-1 factor was achieved pretty well. We went to the European AC main, 374 volts as expected. We were shooting a little higher on the efficiency than we expected, 98.5%-ish instead of the 95, and we also had twice the power density of what we expected, but we could keep the temperature rise underneath the 13 degrees Celsius. We later on made another version of that one where we cascaded 2 of that one and cascaded another converter that we actually could drive an LED application straight from this converter. Thank you very much for your interest.
Thank you. Any questions?
Sure.
I have 2 questions.
Sure.
One is fundamental. To charge the capacitor, you waste the energy, which is voltage squared times the capacitance. But the energy stored in capacitor is voltage squared times the capacitance divided by 2, which means that the efficiency is maximum 50%.
Nope, because you keep the ripple very low.
Can you explain?
Yeah, you keep the ripple pretty low. So the power you're wasting here, if we go back all the way to the waveforms of the, for example, output capacitor. So the energy you're wasting in the switches here, in the on resistance of the switches, depending on which one you have turned on, is the delta V here. So it's the ripple. So the bigger you make the capacitance, the lower the delta V gets, and you square the delta V here and multiply it by the capacitance. And then the story isn't that easy, because the capacitances, if you look also on what all the parasitic ones you include here, they are very nonlinear. So it actually starts to get a linear relationship with voltage. But that's just because the capacitance it can be nonlinear.
And the second question is practical.
Sure.
You are claiming this is LED driver. And in order to drive LED, you need current.
Yes.
So what is the efficiency in case you are talking not about the output voltage, but you are talking about the output current? Because the variation will be in the forward voltage of the LEDs.
Yes.
And how you handle it.
And also the temperature of the LED, the lighting temperature would vary very
I'm
much.
just asking
You definitely want a current there. I totally agree. You definitely want a current through the LED. And this is the first stage converter. We make two switch caps in zeros. So the one was dividing by a factor 2, the other one another one by a factor of 2. So we divided by a factor 4. And then the downstream converter was a resonant converter, which was actually the LED driver. So this one was a current output. So it's a multi-stage.
The feedback is from the current.
Yeah.
And how you measure the current?
We measure the current through an extra winding on the inductor on the resonant converter.
Okay.
You're welcome.
No questions? Okay, thank you. So the set presentation is from Poland. Yeah. Yes, Mr. Damian Jackson. Evaluation of the accuracy of ADAS module readings based on analysis of transient supply current and neutral network application.
Okay, thank you, Mr. Chairman, for introducing me here. My name is Damian Grzechta, and I'm going to give you a few information about how we check the ADAS modules based on the observation of the current supply. This work is done by Paweł Rybka and Krzysztof Paszek. They are PhD students at the Silesian University of Technology in Gliwice, Poland. So the agenda is here. Okay. At first I will tell you a little bit about the main idea of the accuracy of ADAS modules, then how we invented the idea, how we evaluate modules readings reliability. After that, our approach of data processing, it's quite obvious and very simple, but the most important here is how we process the data and what we would like to obtain at the end. And then the data processing with or classification with KNN and Cascade-forward neural network. And after that, the reliability assessment of the ADAS modules. We have a very good speech today about ADAS and about advanced driver assistance systems and different level of autonomous drive. The main problem comes from the modules that are associated with car, like cameras, radars, V2X communication, and LiDARs, because they all communicate with the parent system, like a root system, but we are not quite sure whether these particular ADAS modules are really the ADAS modules that were implemented by the manufacturer. Because sometimes we can replace the radars, cameras, or it can be our car can be attacked by a terrorist and replace the radars. So in such a case, the radar and the communication through the CAN, the transmission through the cameras, radars will be okay, but the another information that can flow from, for example, current that is drawn by a particular module can be another information that prove whether this module is really the module that is inside the car. So we cooperate with industry, and the problem is really serious if you take into account, for example, aging process. If you take into account thermal processes, like if we have very high temperature, the aging process is faster than in normal condition. Depends on country, depends on where the car is, where is the destination of the car. So, is there any alternate solution? So, we found there is no alternate solution for making sure that the ADAS module that is inside the car is really that one that it seems to be. Why it is important? Because it's we do not change the ADAS modules. We implement additional current measurement circuit at the input of the ADAS modules, and the procedure starts when the driver gets into the car. So if we get into the car, then we want to evaluate whether all the modules are really the modules that have to be inside the car. So with a limited time, we acquire the current waveform of the ADAS modules. We assume 35 or 70 milliseconds that we have to obtain important information to the root system whether the ADAS modules is that one that is really associated with the car. So in order to make sure we make some data processing, we acquire the information from the ADAS modules, the real currents from the modules, and we can see some data processing like naive Bayes algorithm or decimation. Obviously, if we take into account the decimation instead of Bayes modules, the time required for acquiring all data is much longer. Why we do the decimation or naive Bayes? The answer is quite simple. Because we would like to speed up calculations. We would like to make or provide the information faster within a specific period. We also choose the wavelet transform and fundamental half wavelet. We can see different voltages of the supply. And for different voltages, the approximation coefficients vary a lot. So it's very sensitive. The wavelet transform is very sensitive for changes in waveform of current. The basic idea how we check our concept is acquisition of data, different data pre-processing, and after that we classify whether the input waveform is the waveform that is associated with the particular module. So we applied KNN and artificial neural network, and moreover, the artificial neural network provides the voltage of the input voltage to the module, to the ADAS module. Okay, the KNN as a reference algorithm has been designed. We had some roots like main samples, 10 samples for each voltage level from 9 to 15 volts with a step of 0.5 volts. So you can see it here. Here also you can see the differences between different pre-processing and KNN classification. cascade-forward neural network where the input vectors has 26 features obtained either from naive Bayes or downsampling, or based on decimation, or wavelet, acquired from data processing. We implemented 5 hidden layers that was arbitrarily chosen by students. And at the output, we expect the voltage that I said before is associated with a source voltage. So you can see what is the classification drift here between different preprocessing and the output or expected output of the source voltage. So the best results are obtained for naive Bayes here in that case. And here is the table where the data classification error is gathered. So for different classification method and preprocessing algorithms, the best is neural network with naive Bayes, where maximum error is 0.26 volts, and average error for the whole range, step 0.5 volts, is 0.07 volts. That gives quite good accuracy for ADAS modules. Next, mean classification error for different voltages within a specific period, and maximum classification error. The best is also for can be occur for between 13 and 13.5 volts. It's the data obtained are here, or 38 for neural network and naive Bayes. And I think the most important here is the certainty factor, because for the parent system we would like to give a coefficient or something like information whether the data processed by the particular ADAS modules is reliable or not. In order to do this, after the classification, we invented the certainty factor because if the neural network output is close to the real input voltage, in such a case the certainty factor should be high. Otherwise it should be low. We can expect that the module is not particular module that should be inside the car at this moment, or maybe it's damaged, or maybe it is like a fake module implemented by some strange or another person during when it was in the garage. So we collect environment data, and the reliability level has been designed in 3 different ways, as let's say window function, also as a Gaussian function, and binary data, whether the module is okay or not damaged or damaged. That's how 3 functions look like. So we have the linear, it's a triangular function, rectangular one and Gaussian one. And we can see that based on the voltage drift, the predicted reliability value is in this table, is covered in the table. So the Gaussian conversion gives information about how similar is the input voltage to the neural network output. So based on the comparison between neural network output and real input voltage, we generate the certainty factor to the parent system. Okay, so the presented approach shown that evaluation of ADAS modules is possible based on the initial transient current analysis and neural network application. there appear to exist more than one way of classification that's quite obvious, and pre-classification, which shows the method versatility and creates a field to develop in the future. The best combination up to now is feature extraction and classification methods in naive bias with cascade-forward backpropagation neural network. And the shown idea itself may be considered as a step toward using the current analysis and heuristic algorithms in the devices and equipments diagnosis, a rapidly growing engineering field in the industry 4.0. And what is worth noticing is the fact that the method can be analyzed and classify numerous external conditions. We here only evaluate input voltages, but as I mentioned before, it is also possible to evaluate aging process, because we have to replace some ADAS modules before it fails. It is quite important to monitor such devices. So it is quite like a piece of code that should be implemented in the root system that can evaluate particular ADAS modules. So aging effect, surrounding environment, and I think many, many more. So this is proof that our concept is really working, and I hope we are going to develop much more reliable methods in the future. Thank you for your attention.
Thank you.
When it comes to classification with sensitivity and specificity, more accustomed to present. So I'd like to hear what these values in your case.
Okay, I didn't provide the information about sensitivity and selectivity, but in that case, the sensitivity is very high. I don't remember exactly. The selectivity is not so high as it should be, I think. But on the other hand, the selectivity and sensitivity, it is good information when you have prepared some real data. In our case, it was like a laboratory experiment, and we had only something like a different voltage at the input of ADAS modules.
But there were real voltages taken. The real
Real
modules.
data, yes, real data.
And my second question is, you know that the requirements for the car electronics are really harsh, because you have cold prime condition, you have a lot of wireless harnesses going. So usually the electromagnetic compatibility requirements are really high, because the currents injected, that is the noise that you have on the wires.
Okay, but we do not inject current.
Really high.
Yeah, but we do not inject current. The main reason we are working on this is that we have a module that is already developed by a third-party company, and we associate a small piece of current measurement circuit at the input of this module.
No, my question is such that you should not expect that the currents and the voltage within the car will be so stable as you
That's
have
true.
in your laboratory condition.
Yeah,
So what will happen to the sensitivity and specificity
Yeah.
in such?
that's true. That's the reason it is supporting system. It is not the main system that the root, the parent system, will take the decision. The main reason we are working on this, it's a supporting system for the parent system, because on the CAN communication, the system will be informed whether the ADAS modules has the particular ID number or whether it is working correctly or not. So based on the datagram which is in the CAN, that can be provided through the CAN communication. But our is independent and will support this system. So obviously we have to think about the sensitivity and selectivity, but on the other hand, it is supporting the main system, because the data that comes from the LiDAR radar and
No, you haven't understood my question. I think we should move. The
Yeah, you can
question
discuss
now.
later. Okay, thank you.
So next presenter is from Serbia, Mr. Ivan Kasa. Yeah. And the topic is optimizing FDTD memory bandwidth with using block flow point arithmetic.
Thank you, Mr. Chairman, for the introduction. My name is Ivan Kastelan. I'm actually not here on the list because I'm not one of the authors of this paper, but I came here as the representative of our study group. We are a study group for computer engineering at the University of Novi Sad. I will be presenting to you the work mostly done by our two PhD students, Stefan Pietlovic and Miloš Subotic, under the mentorship of Professor Nebojša Pjevalica. They were researching ways of optimizing memory bandwidth when calculating, for example, the FDDT, which stands for finite difference time domain simulation of electromagnetic field. So I will give you first a short introduction to the idea of the work. Then I will present you the solution they came up to, results, experimental results with their solution, and a few points on future work. So FDTD, finite difference time domain, is actually a numerical algorithm which is used for modeling of the electromagnetic field. Basically, it's like any numeric algorithm, an iterative method, where in each iteration you solve some differential equations and you update the values for electric and magnetic fields. So it is very computationally intensive, but it is also very memory intensive. So the idea of this work was to try to optimize this memory bandwidth, so to try to reduce the number of times we access the memory in order to perform this calculation, because as you know, memory access is very time consuming. So most of the existing solutions were actually based on the PC architecture. So the idea of our PhD students was to try to make an FPGA solution and see if we can get to some optimized result. So basically, the first idea was to try how the regular ways of representing the data work. So on one side we have the fixed point representation, on the other side we have the floating point representation. As you know, fixed point is less computationally intensive than floating point, but floating point has a better dynamic range. It dynamically changes the range based on the size of the value. But both of these solutions didn't provide the best result. So my colleagues tried first to change the number of bits of data which was used, but it also didn't give the desired result. So their idea was to try to use the block floating point. It is a way of emulating the floating point using the idea used in fixed point. So basically, it presents the ground somewhere in the middle. It is less computationally intensive than the floating point, but it has a better dynamic range than the fixed point. So basically, it takes advantages of both ways partly. So the idea of this block floating point is that if we represent the data points in some sort of a two-dimensional representation like here, is to have a single exponent which is used for a block of data. As you know, in the fixed point we don't have exponents. We basically have the same exponent for all data because the point is at the fixed position. The floating point is the other extreme. We have for every piece of data different exponent and the mantissa. So this is somewhere in the middle. We have a single exponent used for the block of data, and then each different block has different exponents. So the idea was exactly to optimize this memory bandwidth, because we get the exponent once and then we use it for the block of data instead for the single data. So here the optimization problem was how big should the blocks be in order to reach the optimal balance. Basically, if we reduce the block size, then we are approaching the floating point solution, because then we have basically, if the block is of size 1, then we have exactly the floating point solution, because each data has its own exponent. If we have just one block covering all data, it's like fixed point. So the optimization problem was to find the right block size to get the best result. So my colleagues did some measurements on different tile sizes on a certain block of data, and they measured the relative error compared to the regular floating point solution. And they also measured the memory bandwidth optimization, once again relative to that floating point solution. And basically what we can see here is, of course, as expected, as you increase the size of the block, as you approach the fixed point solution, then your relative error goes higher, but your memory bandwidth goes lower. And what was interesting here to see is that the memory bandwidth actually doesn't get too much optimized after the certain tile size. So after the tile size of 4 by 4, you don't get much better optimization of the memory bandwidth, and yet you get a very high relative error. So the conclusion of these experiments could be that the optimal block size is maybe 4 by 4 or 8 by 8, because there the relative error is single digit, it's less than 6%, and the memory bandwidth optimization is practically as high as it can get, around 50%. So the solutions, as you saw in the previous table, save up almost 50% of the memory when compared to the initial 32-bit floating point solution, and the relative error is kept under 6%. So this was the FPGA-based solution, as the regular PC implementations did not provide this result. So to conclude, in the future work, my colleagues will work more on the additional optimizations of the algorithms. This was basically the optimization of the memory bandwidth. Of course, you can work also on the optimization of computational computations, and implementation of this solution on a target FPGA platform, and as always, side-by-side comparison with the existing solutions in the real time. Thank you for your attention. I would like to point you to the emails of my colleagues and apologize in advance if I'm not able to answer your question, because I wasn't directly involved with the research.
Thank you. So, questions, please? Linus always have.
What I'm wondering about, it doesn't matter what size of this total exponent block you select, because it is the data which defines what you're putting here, not you. So that's a confusion for me.
You mean the total number of data points in
No,
It
that
is
block
the data
size.
that's supposed to go there. If it is close, if all the data that is stored, if they are close with their exponent values, then you can put it there. If they are too far away, you have 1 in power of 10 and 1 in power of minus 10. How you can put those two in the same block?
My understanding is that when you are making this operation work, each step of the numerical calculation is not far from the previous step. So all of these blocks are closer to each other than blocks which are separated.
Thank you.
On talking about energy consuming, this method against that usual method. Have you did you have some
No, we actually
measurements?
didn't measure the energy.
Simulation?
It was just the number of memory accesses.
Okay.
Any more questions? No? Thank you.
Thank you.
You saved our time. Okay. So the fifth presentation is from Czech Republic. Yes, Mr. Václav Kollak. And the topic is limiting the influence of regulated electric drainage on track circuits.
So good afternoon, thank you, Mr. Chairman. please let me present our paper limiting the influence of regulated electric drainage on track circuits. First short introduction what is electric drainage, because I think most of people doesn't know anything about electric drainage. When we have electric traction like electric railway or tramway, it uses rail as conductor, and because this rail is never perfectly insulated from ground, part of current goes to the ground, and we call it stray currents. It starts be problem when there is some metal device underground, for example pipeline, and current goes to the pipeline and again back from the pipeline. In this area where current goes from the pipeline to the ground, it causes significant electrochemical corrosion, and it is very dangerous for metal. We can stop this process by using drainage. So in most such cases we use any kind of drainage. There are several types of drainages. Direct drainage, it's only conductor. It is very old and obsolete solution. Another solution is polarized drainage. It is like diode. It may be simple silicon diode, or because of voltage drop, it may be some combination of MOSFETs, because MOSFET can work with much lower voltage drop than diode. And the most sophisticated kind of drainage is regulated drainage. It works like polarized plus some current regulation. Older versions have regulation via resistors, and newer versions uses PWM current regulation. For the last 3 years we worked on development of new version of regulated drainage. Here you can see a simplified diagram of this drainage, and this is in reality, it is tested in the city of Ostrava on tramway. Now I think it is still there. We use this PWM regulation, and PWM regulation causes harmonic components in current. In tramway it is no problem, because tramway uses no track circuits, but in railway there are usually track circuits which uses some particular frequency, usually 50 Hz or 75 Hz or 275 Hz. And any current which flows through rails must not interfere with these frequencies. This standard states some protective frequency bands for these frequencies, and states limits of current which can be injected into rails, or lower. The best is no current in this. In this protective frequency band. In steady state, when PWM is still the same duty cycle and so on, there is no problem, because we have, for example, 100 Hz switching frequency, harmonic components are 200 Hz, 300 Hz, and so on. But problem is when PWM duty cycle is changing. We use this 100 Hz frequency. We change duty cycle in 17 control stages from 0 to 16. Control stage can be changed step by step only by 1 degree at the most. Here we can see a waveform. It was measured on tramway. You could see the photo. Here was control stage 0, so it was permanently switched on, and here was control stage 1. It was switching frequency with these duty cycles, switched on and switched off. And here we can see harmonic spectrum for this waveform. Here are protective bands. Protective bands 50 Hz, it is okay. 275 Hz, it's also okay. But in these protective bands, these two components together are higher than limit stated by standard. So for future, now it is on tramway. There is no problem with this. But in future, the company for which we do development of this drainage wants to use it also for railways. So we must find some solution of this problem. We tested, or we are still doing, we are still dealing with this problem. But we tested one of the solutions to use passive filter. When any drainage is connected to rails on railway in Czech Republic, there is always inductor. Inductor between 10 and 40 millihenry, and we suggested to connect in parallel a capacitor and a resistor like a filter. And because we cannot test it in reality because of safety reasons, so we tested it in simulation and also in laboratory model. Here we can see our laboratory model. The model is in some scale. Currents are 1000 lower than in reality, voltages are lower, and so on. And we tested all possible duty cycle changing. And here are results. Without filter, when there was only inductor, all values in frequency protective bands around 75 Hz were exceeded. With filter, it was okay here, but on the other hand, values in this protective frequency band were exceeded. So, result is that for one specific frequency, for example 75 Hz, this filter can be quite good solution of this problem. And for other frequencies, we must not use it. And values of components must be designed particularly for inductor, and which is in the place where it is supposed to operate. That's all. Thank you for your attention.
Thank
The question that's really a serious problem. You are talking about the DC current or the AC load?
DC current.
DC current. Well, for how long distance have you measured this drainage current? Since we observed in the vicinity, in the house located in the vicinity of the train, was indication of electrocorrosion in the plumbing system and everything. It was if you use the plums, metallic plums like copper, something like this, everything was destroyed. Therefore, there is a very serious problem for that. For how distant you measure this current, since it depends on what is inside the air, how many metallic things, something like this. The current flow through metallic pipes.
Yeah.
Have you measured the distance?
No, we measured currents only through drainage.
Okay, very close to the
very close. Yes, we didn't measure somewhere in field or
in the wide area. Okay, thank you very much.
And you said you want to apply it also for railways. But in railway, as far as I know, they have different frequencies. It's not the same frequencies here. I think it's for tram.
No.
There are acoustic frequencies. I think in Poland there is something a little bit lower than 2 kHz. It's a track circuit.
Track circuit.
But it depends on the country.
Yeah.
In
I
Czech Republic,
think so.
we use these three frequencies. Usually, or there were relays from Soviet Union. I think in Poland it were the same.
No, we have different frequencies.
Different,
That's for sure.
Maybe 200. Maybe yes. I don't know.
1.8, 1.86, and we have 8 channels because you have to separate different track circuits.
We have these three, some are 25 Hertz, and higher frequencies are used for so-called track circuits without borders. I don't know special translation for this. But in Czech Republic we use mostly these three frequencies.
But you know, it's a rather old solution, track circuit, because right now we are using something like RTMS system, and it will replace in a near future all track circuits in Poland.
In future will be DC current traction replaced by alternating current traction, and there will be no problem with stray currents.
But this is alternating current.
No, track circuit is alternating current, yes, but current here is DC, and DC current makes corrosion.
All right.
When we replace DC traction to alternating current traction, and in Czech Republic it will be in next 10 years maybe. So there will be no problem with corrosion and no work for us. Yes.
Okay.
Any more questions? And last but not least, also from Czech Republic, Mr. Lukas Lonhammer. And the topic is methods of for extension of tunability range of synthetic inductance simulators.
Thank you, Mr. Chairman, for the introduction. And good afternoon, everyone. I've already been introduced, so now allow me to introduce the results of the research of mine and mostly my colleagues. This is the outline of my presentation. We will start with some introduction, followed by the goals we focused our research on. Then I will introduce the three proposed solutions of this type of the simulator. We have some experimental verifications and fractional order behavior example. Now the interaction. The tunability range of different parameters in case of many applications is rather limited. So we based our work on this and focus our research on mainly tunability extension, and then we focus our work on the control of multiple parameters within the application or within the active element, and lastly reconnectionless reconfiguration of the operational mode, a transfer function depending on the application we are working with. And tunability extension can be useful in case of different circuits like oscillators, active filters, etc., etc. So the goals we focused on, the first one is the introduction of topologies which contain electronically controllable active elements, which allow the extended tunability of the inductance of the simulators in comparison to the non-solution. Next we have verification of the three proposed solutions of the simulator. We've implemented fractional order inductance simulator, and lastly mutual comparison of the proposed solutions. So this is the standard synthetic inductance simulator we based our work on. It has been introduced in the reference specified down below, and this is the relation for its inductance, and this simulator has rather limited range of dependence of its inductance on the driving force, which was the bias current in this specific case, and the dependence was hyperbolic. So this is where we stepped in, and we've supplemented the structure from the previous slide with voltage multiplier. Its structure is here, and this slide presents the first R solution, which is presented down here, which involves two voltage multipliers, and the relation for its impedance is here, and you can see from the relation that the dependence on the driving force is inversely proportional to the quadratic dependence. The advantage of this first solution is that this element, MLT2, is not influencing the frequency features of the resulting structure. The second solution suggests two multipliers connected in the cascade. The relation for its impedance is the same as in the previous case, but in this case we have to take into account the frequency features of this element MLT2 in comparison to the previous solution. And the last solution is based on inversely proportional adjustable resistors. The relation again for its impedance looks like this. So this time we are working with the dependence, which is 1 over 1 minus 4 set that squared. And we have some restrictions for the specific solutions that we have to work with voltage gains less than 1, so we are limited in case of driving force from 0 to 0.25 volts. In case of the verification, we used the multiplier AD835. We set its multiplication constant to 4, so we can obtain max voltage gain also 4. In case of other active elements in the structure, diamond transistors, we've implemented OPA 860 device, and the value of the capacitor in the structure was set to 1 nanofarad, and the values of resistors were 91 ohms, which results in 102 ohms when we take into consideration the input resistance of diamond transistors in the structure. Here we have some results. In case of the first solution, the ideal range of its tunability of the inductance is from 250 microhenry to 2.5 microhenry, when the Vset is adjusted from 0.05 to 0.5 volts. And the simulations we've obtained are quite similar to the theoretical expectations. In these graphs, you can see the dependency of the circuit impedance and phase depending on the driving force we set for different values. Here we have some comparison of our solutions together compared with the original solutions we based our research on. So you can see that in case of all three solutions, we were able to obtain a wider tunability range than in case of the standard or the original solution. And now in case of fractional order example, we replace the capacitor in the structure by the CPE element with this specification, and you can again see the results in case of theoretical expectations, simulations, and measurement for the impedance of this solution and phase for different values of the V set. It's also compared with standard magnitude in case we would use the normal capacitor of value of 1 nanofarad, which is the purple line, and it's compared with the rest. Here we have a table with specific values of the impedance at 100 kilohertz and inductance for different values of V set. First table compares the theoretical expectations and simulations, and the second table compares the simulations and experimental results. Lastly, we can compare our solutions with some other works. And as you can see, our solutions provide the extended tunability in comparison to other works, because the first two solutions we have inversely proportional quadratic dependence on the driving force, and in the third case we have the dependence 1 over 1 minus 4 V set, that's squared. So we are getting to the conclusion. I will just sum the main basic information about our research. So we are able to extend the tunability of our solutions in comparison to the original structure with changing the driving force in all cases in the same range. We've implemented fractional order simulator, and in case of the future work, we plan to implement active elements with different dependencies on the driving force, and application of these approaches in case of impedances of higher order. That concludes my presentation. Thank you for your attention.
Thank you.
Yes?
What I'm wondering, is it so that if the C component of the signal that you are trying to fit, because probably these are used for filtering.
Yes?
So what if the C component of the signal that you are trying to fit will be 15 millivolts or more? How it will be interpreted?
Capacitor. Are we talking about standard capacitor or in case of CPE? Inductance. For higher, we said then 0.5.
Because I see that control of the inductance is 50 millivolts. And probably it is expected that there is no DC bias coming together with the signal. That is, the control of what inductance you get is via the DC voltage.
Yeah, that's the DC voltage, yes.
So my question is, what happens if the DC voltage will come from the AC source that we're trying to filter? But 50 millivolts, it will be enough, because nowadays you are trying to use the capacitance which possess the piezoelectric effect. And if it is piezoelectric effect due to heating, due whatever, 50 millivolts is easy to get from MLCC with large amount of barium titanate. And we are talking about relatively low frequencies, because the frequencies that you can operate is just 1 megahertz and below, according to the drawings that the results that you get.
More or less,
Because
yes.
10 megahertz you are not operating, which means that 100 kilohertz, even the kilohertz and below, are the frequencies you are working with. And in order to have the DC decoupling, as some of the colleagues suggested, you will need large capacitors. large capacitance, nowadays it's easy to get with multi-layer ceramic capacitors. Multi-layer ceramic capacitors, they are made with barium titanate. And barium titanate possesses piezoelectric effect, which means that if you squeeze the printed circuit board, it is producing the voltage. I might say I will not be squeezing my board. No, there is no need to squeeze. You just hit it slightly, it is changing the dimensions, and it is producing the bias. That's why I was asking about 50 millivolts, because 50 millivolts is quite easy.
Yeah, see, well, in our cases, I think we can go from 0 to 1 volt, I think, because
Well, from 0.05, for instance, you will go to 0.01.
Yeah.
No, I'm just curious whether externally appearing DC bias will distort the value of the inductance that you're supposed to get.
well, we haven't. I don't think we have made
So far,
any analysis in this.
simulation, because you are putting exact components, which means that you have done the experiment.
Yeah.
So you haven't noticed such thing.
I don't think we have any further analysis in this matter, so
It's for future.
Okay, any more questions? No? Thank you. So our session is finished. Thank you all speakers and all listeners. And now it's time for coffee break. We fit in time almost like just on time.